Hi, everybody. We're back with part two, and we're here to talk about which model to use. So we have three choices: a linear model, a quadratic model, or an exponential model. So the linear model is pretty well known. You guys have been studying that for quite a while. And we just did a pretty extensive look at the quadratic model. And the third choice is the exponential model, which we haven't seen in a while. So maybe we should just take a little bit of a tangential detour and talk about exponential models just for a minute. Okay, exponential models have a standard form, a times b to the x. A is the initial value. In other words, when we graph this, let's say it's exponential decay. A lot of times the x value, where x is 0, will start. So this value right there we call the initial value. That is A. It's also, of course, the y-intercept. It's the value of the function when x is equal to 0. If we look at the function, and let's get rid of some of this stuff. F of x is a times b to the x. And if x is equal to 0, we put in 0 everywhere we see x, a times b to the 0. But that's a times 1, because b to the 0 is equal to 1. And of course, that's a. So when x is 0, f of x is a. That's our y-intercept. F of 0 is equal to a. Okay, so that's a. Now let's take a look at b, the base. This is what we call like growth factor or decay factor. If the base was greater than 1, it grew, and if the base was between 0 and 1, it was decay. And of course, no bases are negative, nor 0, nor 1. A quick little example down here, f of x is 3 times 2 to the x. I made a table and I had x go up in equal increments to make sure that the change in x was always the same. We go up by 1 every time from -2 to -1 to 0, all the way up to 2. I just calculated what y was, what f of x was when x was, for instance, -2, y was 3/4, and then when x was -1, y was 3/2, etc., all the way down the table. Notice each time we are multiplying by 2, times 2, times 2, times 2. That's typical of an exponential function because you are multiplying every time x goes up by 1, you're multiplying by 2. So 2 is the common ratio. These exponential functions generate a list of numbers y that is in geometric sequence. Another name for 2, of course, is the growth factor. And 3 is our initial value, the value of f of x when x is equal to 0. Okay, so given a set of data, can we write the function? So here's our set of data. So we're given this table. Well, notice that every time as we go from one point to the next point to the next point, we are multiplying by 3. This is indicative that this is an exponential function. So we know that the standard form is a times b to the x. It's going up with a common ratio of 3. This is a geometric sequence. My common ratio r is 3. That's the base. So my base is 3. I know that when x is 0, y, or f of x, is 4. So in other words, my y-intercept is at y is 4. So now I have everything I need to know. A is 4, b is 3, and f of x is 4 times 3 to the x power. So we really do need to take a careful look at the data to determine which model that we need to use. We need to see, do we have a common difference, a common ratio? Let's see what we have here. So we have a table. Once again, we're given this table, and we're asked to find the equation that fits it. And notice that every time I'm multiplying by 3/4 times 3/4 times 3/4. So my common ratio is 3/4, meaning once again, it's exponential. Now my common ratio, the base, is 3/4. We have a base that's less than 1. This is going to be exponential decay. So my typical curve I know that when x is 0, y is 25. Therefore, my y-intercept is at 25. My decay factor, r, is 3/4, and I'm able to write my equation. Okay, another set of data. This time I notice that every single time we're going up by 3, up by 3, up by 3, every time. That's indicative of that's an arithmetic sequence that's formed, and that's indicative of a linear equation, a linear model. So the x is equal to 0 and y is 5. That's our y-intercept. My common difference in that arithmetic sequence is 3. That's my slope. So my slope, mx plus b, 3x plus 5. So we looked at the differences in f of x. We looked at the differences in the output, the function's output, f of x. And in this case, every single time the difference was 3, and that is a linear model. Okay, another table, here we go. So you're given that table. And now you're looking and you say, okay, what's the differences here? First of all, is there a common ratio? Can I multiply to go from 8 to 0 and then to -6 and -10? And the answer is no, especially at the 0 point. Once you get at that point, anything you multiply by will be 0. Okay, so it's not exponential. Let's see if it's linear. Can we add the same thing every time? Add 8 and then 6 and then 4 and then 2? No, we have this set of numbers, 8, 6, 4, and 2, all different. The differences aren't the same. But what about the differences of the differences? In other words, the difference between 8 and 6, between 6 and 4, and between 4 and 2. And notice that they're all equal to 2. The difference of the differences, what I'm going to call the second difference. Our first difference was right here. And now we'll say the second difference is this list of numbers, and it's all equal to 2. When your second differences are the same, in this case it's 2, you have a quadratic model. And in this case, I got that data from the table from that quadratic equation. So this idea of differences, the first difference being the same means it's linear. The second difference being the same means it's quadratic. Let's see a couple of more quadratics. Here's my equation, x squared minus 9x minus 52. I filled in my table. I found my set of first differences went from 12, 10, 8, and 6, but my second differences are all the same. Yeah, it's quadratic. Of course it is. That's what we started with. And down here, the same thing. My second differences ended up being the same. So to wrap it up, linear, first difference is the same. Quadratic, the second differences are the same. And exponential is when you multiply by a common ratio to go from one output value to the next. Open up your books and take a look at number 27 on page 594. Give that a shot in your notebook, and hopefully you'll see a pattern that will be easy to understand. Take care and be well.